Hello, I'm Hassan Hussein and I'll be doing the introduction and outline of Sharp.ml. And our team's topic is optical second harmonic generation in anisotropic multilayers with complete multi-reflection analysis of linear and nonlinear waves using Sharp.ml package. Second harmonic analysis of anisotropic rotational polarimetry in multi-layers, Sharp.ml, is an open source software package designed to address the limitations and approximations commonly employed in existing analytical approaches for studying nonlinear optical phenomena, specifically focusing on second harmonic generation multi-layer structures. SSG is a nonlinear optical effect used in lasers and such. The software offers several key features and improvements, such as closed form solutions. Sharp.ml provides closed form analytical solutions for crystals with arbitrary symmetries, orientation, and anisotropic properties. This capability is crucial when evaluating the optical responses of new materials for which optical properties are not known in advance. And multi-layer structures. Many optical components like slabs, thin films on substrates, and multi-layer heterostructures involve multiple reflections of both the fundamental and up to 10 different SSG waves at each interface, which we'll see. Sharp.ml is designed to handle this complexity and provide accurate results in such scenarios. And elimination of common approximation. Current techniques such as Maker's fringe SSG polarimetry uses multiple approximations such as slowly varying approximation, weak reflection of nonlinear polarization, transparent medium assumption, high crystallographic symmetry, Kleinman symmetry, phase matching conditions, and negligible interference among nonlinear waves. By removing these approximations, Sharp.ml aims to provide more accurate results. Reliability and accuracy. The software's reliability and accuracy are established through experimental benchmarking. It is compared with both SSG polarimetry and Maker fringes, which are predicted using standard materials. This comparison ensures that the software's predictions align closely with real-world experimental data. We'll move to the introduction now. And optical second harmonic generation refers to the nonlinear optical process where two photons of h bar omega energy are destroyed and a photon of 2 h bar omega is created in a nonlinear optical medium. This phenomenon is described by the nonlinear polarization P2 omega is equal to chi2 e omega generated in the NLO material at 2 omega frequency by the electric field of the incident light E omega at frequency omega. Here chi2 is second order nonlinear optical susceptibility represented by the third rank tensor with 18 independent components, D tensor. If the refractive index and chi2 tensors of crystal are known, one can employ numerical simulations to model their nonlinear optical responses. However, for new materials with unknown optical properties, experimental responses need to be measured and modeled by analytical or semi-analytical approaches to determine the coefficients by fitting the models to the experimental data. The complexity increases when plus the unknown chi2 tensor, we have birefringence, arbitrary crystal symmetry and orientation, complex dielectric function, etc., etc. And large errors in chi2 may be mistakenly introduced if the analysis is not handled properly. In particular, currently we have Maker fringe technique, and this has become the primary method for characterizing nonlinear optical susceptibilities in transparent crystals, where the transmitted intensity is measured as a function of incident angle. Further advances have been made, extending its applicability towards uniaxial systems and biaxial materials cut along high symmetry directions. However, these characterization methods are generally limited to transparent systems with high crystallographic symmetry, P and S polarized pump, and SHG waves, and relatively simple geometry such as a bulk single crystal, a single crystal slab, or a single crystalline film on a substrate. SHG polarimetry is another technique to map out the anisotropic chi2 by varying the fundamental and second harmonic polarization states of light, which is applicable to both transparent and absorbing crystals. Nonetheless, both Maker fringes and SHG polarimetry uses many assumptions, and this could cause high errors in chi2. In this work, we present a comprehensive theoretical framework and an open source package Sharp.ml, which stands for Second Harmonic Analysis of Anisotropic Rotational Polarimetry for Multilayers, for modeling second harmonic generation in an arbitrary single interface and complex heterostructure with full consideration of multi-reflection at both linear and nonlinear frequencies. The Sharp.ml is designed to provide numerical and analytical nonlinear optical solutions for both simulation and experimental characterization, allowing for fast, flexible, and user-friendly analysis of nonlinear optical response on complex material systems. 5 key attributes include ability to model a multi-layer stack, allowing arbitrary crystallographic symmetry, orientation, and process absorption as well, birefringence and dispersion of each layer, choices for both reflection and transmission probing geometries, full control of polarization states of incident and detective waves, and explicit consideration of the multi-reflection of both linear and non-linear waves. We have done case studies of 6 material systems, which we'll see later on, to show the reliability of this package. Now we'll move on to the theoretical background and how the sharp-to-temple processes the information. Figure 1a presents the ray diagram of linear and non-linear waves through a multi-layer system adopted in sharp-to-temple. Without loss of generality, we assume the first layer M1 to be SHG active. So in this figure, this is the figure with multi-layer, and we assume M1 to be SHG active. And then when a monochromatic plane wave at omega frequency is incident upon the system, the electromagnetic properties of the plane wave inside the system are governed by the wave equation at omega frequency. Here E omega is the electric field at omega frequency, epsilon omega is the anisotropic dielectric tensor at a lab coordinate system, and mu omega is the magnetic permeability. And epsilon can be complex to account for absorption. 4 coordinate systems are utilized, namely principal coordinate system, crystal physics coordinate system, crystallographic coordinate system, and lab coordinate system. In principal coordinate system, the complex dielectric susceptibility tensor is diagonalized. In crystal physics coordinate system, the property tensors are defined, such as dielectric susceptibility tensor, SHG tensor, piezoelectricity tensor, etc. CCS or crystallographic coordinate system describes the coordinate system formed by the basis vectors of the unit cell, and lab coordinate system is formed by the the plane of incidence, which coincides with the L1 L3 plane. So this is the plane of incidence, this red plane, and L1 L3 which coincides with it, and this forms the lab coordinate system. And here PCS, ZCS and LCS are orthogonal, but CCS need not be orthogonal because it depends upon the crystal symmetry. And due to reflectance at various interface, both forward and backward propagating waves exist in the heterostructure. The resulting backward propagating wave vector can be described as KEB omega, KOB omega at different layers with respect to the forward waves. E is extraordinary, O is ordinary. And now we apply the boundary conditions for continuity of the tangential components of both electric and magnetic fields at an interface between different media. The boundary conditions for the tangential components follow from Maxwell equation. At Z is equal to 0, which is at the interface. This equation holds for both electric field and magnetic field. And from this we can infer that EXI plus EXR is equal to EXT, and EYI plus EYR is equal to EYT, and similarly for magnetic fields. Now when we substitute the complex electric fields in this equation, we get this equation, and here e raised to omega t gets cancelled out. Z is 0, so that term is not there. And this should be satisfied for all points x and y. So we get kxi is equal to kxr is equal to kxt, and kyi is equal to kyr is equal to kyt. Now applying these boundary conditions to our present situation, we get these equations. Here the wave vector, incident wave vector, reflected, transmitted, and wave vectors in between the layers, and then electric field at the first layer. First layer we have the incidence and the reflected, and yeah, extraordinary forward, ordinary forward, extraordinary backward, and all the electric field equations between the first and last layer. And then the last layer we have the transmitter electric field. Similarly, same thing for magnetic, and this is H as well. And phi is the phase difference. Phi is the phase difference for a forward wave propagating from top to bottom surface. And these are all parallel to the surface. These are tangential to the surface, electric field and magnetic field. And now we move to the non-linear polarization, which is defined as P is equal to epsilon naught chi 2 e omega e raised to I ksr minus 2 omega t. Here ks is the wave vector of the source wave, r position vector. And since arbitrary layers can be SHG active, P2 omega can be 0 for different MIs. And the propagation of nonlinear waves is governed by the wave equation at 2 omega, which is the wave equation. And this highlights how the nonlinear polarization created by electric fields is omega creates the electric field at 2 omega frequency. And the solutions to this equation form the bound waves or the inhomogeneous waves, and the waves formed by the bound waves form the free wave or the homogeneous wave. And the anisotropic three-wave mixing phenomenon is revealed in equation 10. When material anisotropy is taken into account, in each SHG active medium, the forward and backward nonlinear wave vectors can thus be identified as the ks 2 omega is equal to 2 kef omega, which is basically like e extraordinary forward, extraordinary forward. So you get 2 kef, and we get 2 kof when it's ordinary forward, ordinary forward. Similarly, we get like that 10 terms, and we denote it in this way for mi, which is different layers. And a nonlinear polarization PEF OB 2 omega will be a nonlinear polarization formed by extraordinary forward and ordinary backward. And the wave mixing terms containing both forward and backward waves such as KEF-EB and KEF-EB and KEF-OB, KOF-OB, are often dropped or ignored due to large phase mismatch. But these terms form standing waves propagating parallel to the layers. The standing waves at both the top and bottom surface of each layer can still contribute to the boundary condition, and thus Sharp.ml has implemented these mixing terms. At most 10 distinct nonlinear polarization of different combinations of wave vectors for each SHD active layer. These 10 waves are shown in 10 different arrows in figure 1a. These three, and these three, these four. And all electric and magnetic fields generated by the 10 distinct nonlinear polarization can be uniquely identified by solving equation 11. On the other hand, the general solution of equation 11, which represents the homogeneous waves, can be calculated following the same procedure as solving equation 1 but at 2 omega frequency. Equation 1, which is just wave equation at omega frequency. With 2 omega frequency, we will solve, and we get 4 terms: extraordinary forward, extraordinary backward, and ordinary backward at different layers mi, whose field strengths are determined using the boundary conditions to be described below. So these are the same boundary conditions as before, but for 2 omega. And yeah, at first layer, all the layers in between, final layer, we have like 14 terms, two sides of the equality. Similarly for magnetic field. For a non-SHD active layer, the polarization term will be 0, so all the inhomogeneous waves will be 0, but there will still be homogeneous 2 omega waves. The SHD measurement geometry is shown in figure 1b, where the incident light is focused on the surface of the sample, and the generated SHD response can be collected in either transmission or reflection geometry. So the red is the incident and blue is the reflection and transmitted. And yeah, two common techniques can be used, as said before: SHD polarimetry and Maker fringe method. SHD polarimetry, both the incident polarization, SHD polarization can be varied to probe the polarization dependent anisotropic SHD tensor. This method provides more comprehensive information on the anisotropy than the Maker fringe method and can be utilized to identify the orientation of point group symmetry of a crystal. On the other hand, the Maker fringe method measures the transmission SHD as a function of incident angle with fixed polarization directions of both the incident and the SHD waves, such as P or S polarized light waves. The variation in the envelope of the SHD intensity versus the incident angle can reveal the relative magnitude of nonlinear susceptibilities. However, the transmission geometry for Maker fringes limits its application to material systems that are transparent. Sharp.ml can model both the SHD polarimetry and Maker fringes numerically or semi-analytically, which can be used to determine the unknown SHD tensors of new materials. Now we'll move to the outline of Sharp. The theoretical method described in the preceding section is implemented using Wolfram Mathematica, and figure 2 shows how it calculates. We put the input parameters: crystal structure, orientation, dielectric tensor, refractive SHD tensor, the wave equation at omega frequency, boundary condition, non-linear polarization, and the wave equation at 2 omega frequency. You get the inhomogeneous waves, 10 terms, homogeneous waves, 4 terms. Then we apply boundary condition, and we get the ET and ER, the transmitted and the reflected electric field. The obtained sets of field strengths are the result of multiple reflections of the pump frequency. The generated nonlinear polarization vector can thus be obtained from electric fields at omega frequency. Further solving the wave equation, the nonlinear frequency can provide the wave vector and electric field directions of all forward and backward homogeneous and inhomogeneous waves in each layer. 14 waves for nonlinear optical layer and 4 waves in the non-NLO layer. Finally, plugging all the waves at 2 omega frequency in the boundary conditions of electric and magnetic field gives transmitted and reflected polarization and resolve nonlinear optical response. So this is the introduction, abstract, and the working of Sharp.ml. Now we'll provide case studies to show the reliability of Sharp.ml. Thank you.
Hello, sir. Myself, Soham Mandal. I'll be explaining one of the case studies of maker fringe patterns for alpha quartz. Okay, so here we are trying to show the capability of SARP.ml, the package, that how it is capable to reproduce the SAG data from the analytical models available in the literature. So the two main models which we will be using here, and it is also widely used. So one is JK method, Jeb Hagon and Kuj, they are two scientists, and another is HH method, that is Harmon and Hayden method. So in these two methods, the first one, the JK method, they did it for isotropic medium only, and they also took the assumption that they will be considering forward propagating waves only. But the HH method is kind of, you can say, some little bit of advance of JK, because they considered the birefringent uniaxial system. So what exactly the birefringent means? Birefringent means it is a optical property of a material, that the refractive index of that material will depend on the polarization and the propagation of the light. They considered this kind of material, and also they considered the forward as well as backward propagation of the homogeneous waves, means that is they considered multiple reflections also. So here our main focus will be that how SARP, this package, is capable of reproducing this data given by the JK method and the HH method. So here is the main graph. So here are three graphs generally colored in three different colors. One is analytical HH, other is hashtag SARP-JK, hashtag SARP-HH. So what does it mean? This analytical HH means this graph, this blue graph was plotted. This blue graph was plotted by the experiments by using 300 micrometer X-cut quartz, X-cut uncoated quartz, obviously. Yeah, and then the all the same datas are had been fed to the SARP.ml, and considering each method's assumption, means in SARP JK we did the experiments in the software by considering the assumption of the JK, and in the SARP HH we did the experiment of the SHG by considering the assumption of the HH, and we will try to see that how it is, means how it looks like as compared to the analytical HH. Through the graph B, we can see that it matches quite good with the analytical HH, and it so this also proves one thing: the capability of SARP. The capability of SARP, we can say that it can reproduce the data, analytical data, what you get from the observation, very good, and especially the analytical HH and the SARP HH matches very nicely. The pattern, all that matches very nicely, which we can see in the magnified version. This blue one is the analytical HH, and the green one is the SARP HH. We can see that they're matching quite good. And one more thing we can say here, that the at the yeah, and one more thing, yeah, this graph has been plotted with the SAG intensity and with respect to the incident angle, with respect to the incident. And here we can see it in the graph. Wait a second. Yeah, here is the theta I is taken with respect to this perpendicular, and the coarge is x cut coarge. And yeah, one more thing, the x cut quartz means the crystal quartz has been cut perpendicularly to the x axis, means it is cut along the yz plane. So that's some basic understanding of this. And the what analytical experiment we did using this X-cut quartz, and the fundamental wavelength is 1064 nanometer, and this is a X-cut uncoated quartz. Okay, that's it. That's fine. And one more thing, all these three maker fringes patterns matches quite good, and we can say that yeah, SARP is doing very well. One more thing, we can also see a basic difference in JK and HH, obviously, because these two method has different assumptions of showing SHG responses. So in the magnified portion here, the dashed portion has been magnified here, and it is the incident angle is I think around 20 to 30 degree. So if we magnify this portion, we can see that this sharp HH is totally different from the sharp JK, which is what means why it is different. The main reason it is different because HH considered the propagation of forward and backward waves. Because of that, multiple reflections occurs, and due to multiple reflection and the interference of the forward and backward propagating waves, the amplitude increases. So that's why the amplitude is sometimes increasing, decrease, because there is constructive and destructive interference as well. So from this we can conclude that yeah, SARP is doing pretty well, and it's not pretty well, it's matching very nicely with the analytical experiments. One another thing, we'll be demonstrating the full multiple reflection of the Z-cut quartz, the Z-cut uncoated quartz, to determine the nonlinear optical responses. Means we will see what happens when you consider full multiple reflections in the Z-cut quartz. And here also the Z-cut quartz means that quartz crystalline, that is SiO2, that is cut along the YZ plane, and that is XY plane, and it is perpendicular to the Z axis. So that's the thing. So here also this here we will talk about the full multiple reflections. So generally what is happening in full multiple reflections? So in full multiple reflections also, as the quartz, the crystalline, is not a good reflecting crystal compared to many available in nature, or many available, its reflectance is very poor. So all of the four all of the four maker fringe patterns, what are the four maker fringe patterns? That is one that is defined from the experiment. We did experiment by passing a wave of 800 nanometer through a Z-cut quartz. That is the experiment we did, and we compared its SHG responses with the incident angle of the fundamental wave. So that is the experiment. Another is that SARP JK, means we consider the JK assumption, and we implemented in SARP, and we also considered the HH assumption and implemented in SARP. And another is SARP FMR, means we implemented the full multiple reflections in SARP. And one more thing I forgot to tell, that SARP is capable of showing SHG in multi-layer, and linear and non-linear waves as well. It means that and the SARP.ml, that ML stands for multi-layer. So that's a thing, that's the fact that SARP is capable of for a wide range of crystal, means wide range of materials. So, and yeah, coming back to the point, due to the weak reflectance of the quartz, the from a broader view, we can't distinguish the graph. We will say, yeah, this is the experimental graph, and yeah, this is the SARP JK, SARP HH, and this is the SARP FMR. But if we zoom in at the particular position, means that what we have done in the dashed region here, when the incident angle is around like 30 degree or something, if we zoom in, we can see some fine fine fringes. Fine fringes. Why this is fine? Why there are fine fringes? Fine fringes are due to fmr. So what, why this is fine fringes is happening? The fine fringes is happening because the forward and backward propagating waves that 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 does reflections, and due to the reflection interference happen, and due to the interference the amplitude increases and sometimes decreases in the corresponding directions. So this is full multiple reflections all about, and this is all about the capability. Means not all about. Is it shows that how the SARP is also capable of showing analytical things in the form of numerical analysis. So that's it from my side, and thank you.
Talking about the topics and registrar construct. Hello, I'm Richie Shambarkar, and I would like to continue the topic of alpha quartz crystal. Now we're going to talk about the quartz crystal with a gold coating. It basically says that you kind of add a thin layer of gold, like a gold foil, on the existing alpha quartz crystal. The foil is approximately 1.9 nanometers in length, and this also causes a high efficiency reflection. So the light coming in, the particles coming in, the photons uh, have a high reflection, have a lot of reflection. So this results into backward propagating waves, and the ratio of the backward propagating waves here is higher than the regular alpha quartz crystal. Uh, so this results into a proper FMR, which is a full magnitude reflection. This is talking about our curve. So in this example, we're going to look at the hashtag sharp FMR plus I to the power I superscript theta superscript I plus h plus lambda superscript omega. So we pass a we pass the omega frequency, and due to second harmony generation we get two frequencies out. That's pretty standard. So what we want to look over here is at the green line, which their program sharp.ml produces. So the green line is what it produces, and the black spots on it are what the spectral results for. And as you can see that this is very very close to it. You could say it's almost entirely a subset, and that's really very nice. So it gives us a very uh, proper result. And in this case, we only vary the angle to about 40 degrees. After that, the calculations are not very very, you could say, accurate. That's where in this model we only vary to 40 degrees. And now we're going to compare it to the regular one that we observed last time. So last time we observed that without the gold coating, this is the kind of pattern that we get, and with the gold coating, this is the type of pattern that we get. As you can see that in this one there are three maximas and two minimas, and the other one there were just two maximas, and you could say one minima. It's like a big minima, so I don't really know what to call it. But uh, this is kind of pretty much expected, because even in our approximated eigenvalue problems that we are very much used to with all the approximations, we usually get a summation of two waves, and that is what happens with the regular case. And now that we introduce our um, we now that we introduce a gold coating, we are kind of getting another wave. So this was kind of a little bit more expected, as we're getting three peaks. And okay, continue forward. So as you can say, one can say that uh, this is basically like a result we get from the top of the mind that comes is that if you take the regular FMR, it doesn't really have that. Uh, it doesn't really have those spikes at very high frequency with. One could say if we could just take a low pass filter of it and just filter out the higher frequencies, probably we could get the same result. But because I think this usually happens due to the high fluctuation of theta at very uh, minuscule changes anyway. So from this curve, we kind of get the um, how the how we can kind of see the imaginary refractive index change as we change the wavelength, and this is also plotted using the sharp.ml function. And lastly, I would like to get to a point at how the thickness of the material matters. So, what happens is when you even change the thickness a little bit, even according to the calculations, what results you get are extremely different from what we are expected to get. So, we could say that this is very sensitive to a distance. And yeah, I think that's pretty much it. Okay, thank you for your time. Uh,
Hello, I'm Ihsan Hussain and I'll be doing the LINBO3 and KTP single crystals case study. LINBO3 and KTIPO4 are two crystals that have been extensively researched because of their impressive nonlinear optical properties. They have well-documented characteristics that make them ideal for comparative analysis. By using the partial analytical expressions generated by Sharp.ml, we can analyze experimental data from polarimetry to determine the relative ratios of SHC coefficients. Additionally, we can calculate the absolute SHC coefficients of these two crystals by using alpha quartz as a reference material. KTP adopts an orthorhombic crystal structure with a point loop of MM2, which is 1, 2 for lateral tube, usually perpendicular, mirror links parallel to it. It is classified as a biaxial material with distinct optical responses along all three crystal physics axes. Thus, a careful analysis of full anisotropy and the presence of two optical axes are critical in optical modeling. In this study, we used two KTP slabs simultaneously, namely 370 micrometer X cut 100 orientation slab and 570 micrometer bipod 010 orientation slab to analyze the full SHD tensor. Both C axes are placed along the L2 direction and the optical axis lie in the L1 L3 plane. We can see that the C axis is along L2 direction for KTP, X-cut and Z-cut. POI is the plane of excellence and L1 L3 is the optical axis. Uh, Now we can see the SSD response in sharp.ml. This is the sharp.ml page. It runs on Mathematica. So if I go to set material properties and I select L9 geometry, I can choose the slab thickness and update. Now it shows the coordinate axis. I can get the SSD simulation. Unfortunately, the makeup in this plot and Fresnel coefficient plot doesn't work. There seems to be an error in this version. But for FMR over backward standing waves, then I can choose the angle 15 degree and now we can see we have bar diagrams that show the SSD coefficients for aligned unity and KTP for different cases, sharp rotatable and climate symmetry, no multiple reflections, and no forward backward wave mixing. And we can see the variations. And like in this case, we can see sharp rotatable is very similar to NMR, and in D31, 32, the error was very high when we assume climate symmetry. We notice the possibility of errors in our calculations of nonlinear optical properties, particularly the second harmonic generation coefficients, when we rely on symmetry assumptions such as isotropic materials. These errors can be quite significant, potentially reaching up to 30%, so like here with climate symmetry, when dealing with materials that exhibit anisotropic properties. To address this issue, we consider three factors: climate symmetry, uh, exclusion of multi-reflected linear and nonlinear waves, and the omission of nonlinear polarization resulting from the combination of forward and backward waves. Sharper memory allows us to selectively incorporate or exclude these factors during our modeling and analysis, like we saw. Uh, we can choose between full multiple J and K, H and H, forward, backward, forward plus backward standing, giving us valuable insights into the impact of symmetry assumptions on our calculations. Above bar diagram summarizes essentially coefficients ratios obtained under different assumptions to fit the same experimental data for aligned verification respectively. The climate symmetry assumes all three pieces in the D tensor are permutable, leading to D3115 equal L. D31 is equal to D15 in Li and PO3, and D31 equal to D15, D32 to D24 in KDB. The NMR case is equivalent to the HH method, where only multiple reflections of the nonlinear homogeneous waves are considered. The no PSP case neglects the nonlinear polarizations generated by one mixed forward and backward waves, that is extraordinary forward, extraordinary backward, extraordinary forward, ordinary backward, ordinary forward, extraordinary backward, ordinary forward, and ordinary backward cases. The sharp or dimple case represents the analysis with full consideration of multi-reflection of linear and nonlinear waves or possible nonlinear polarizations and complete material anisotropy and no climate symmetry assumed. Comparing the four cases, we found most of the obtained SSD ratios vary between 20 to 30%, which are commonly comparable to the error path, as we've seen. Uh, the NMR case is close to sharp rotatable case, implying that the HH method may be a good approximation for studying KTP with photorealistic zero-based band gap. The KS case, however, can introduce relatively large deviations in the obtained coefficient ratios, such as 60% for the pre-1 pre-2 case in KTP. Huge error with climate symmetry assumption of climate symmetry. And using partial analytical expressions generated by Sharp or Temple, the SSD polarimetry fitting show good agreement between theory and experimental data, and the extracted ratios and absolute values of SSD coefficients KTP are summarized in below table. We can also obtain partial analytical expressions from here. We can get the homogeneous states, two omega homogeneous states and omega homogeneous states reflected and transmitted. And we can get the partial analytical expression from Sharp or Temple. And comparing for LINVO3 slab and KTP slab, the SSD coefficients from Sharp to Temple and from experimental data, we can see the error was very less, and thus this shows Sharp to Temple is highly reliable. And that will be it for me. Thank you.
Hello sir, this is B. Shiva. Today I am explaining a case study that is ZNO platinum Al2O3 thin films. So ZNO has been a subject which has many years it done research due to significant applications in electronics, photonics and optoelectronics. This is because of its notable characters such as it has large piezoelectric coefficient and substantial extron binding energy and wide optical band gap and excellent chemical and thermal susceptibility. In recent years, ZNO is combined with magnesium. It has demonstrated some kind of ferroelectric properties. So It shows some kind of promise material for application like waveguides and quasi phase matched frequency conversion device. So, and nonlinear optical processing ZNO has been thoroughly investigated in both bulk and thin film forms. However, there is a wide range of report values for nonlinear optical susceptibilities, and it's ranging from less than 1 picometer per volt to 100 picometer per volt. This variation suggests that it is either difference in sample used or inconsistency in the modeling of second harmonic generation SHD data. And they have chosen a specific material configuration like a 159 nanometer layer of zinc oxide which is placed on top of 200 nanometer of lith layer of platinum, and both which are deposited on 0.5 millimeter thick substrate of aluminum oxide. This configuration separates a thin film ZNO on a substrate of Al2O3 with a bottom electrode PT. As described earlier above, ZNO is growing using RF magnetron sputtering and formed a stack of ZNO PT Al2O3 as shown in figure. Like this is how it formed, and the wavelength is a center of 15 nanometers and incident angle is around 45 degrees. The reflected P and S polarized SH intensities are at 775 nanometer are then collected and functions they functions as a incident polarization. Epiaxial ZNO film adopts a Wurtzite structure pointing group 6 millimeter and remain isotropic within the plane direction. Epiaxial means these films have a crystal structure that aligns very closely with the crystal structure of substrate, and Wurtzite structure is a specific arrangement of atoms in a crystal lattice, and it is common structure for ZNO. And pointing group 6 millimeter is a symmetry designation indicating the symmetry of crystal structure. And isotropic is it means that properties or the characteristics of ZNO films are same in all directions within the plane of the film. Now we are going to figure B. It shows crystal structure of ZNO and its crystallography direction related to lab coordinate system. Those are Z1, L1, 13. Due to strong reflection of PT bottom electrode, the fundamental wavelength of 1550 nanometer and SHG wavelength at 775 nanometer. It shows the multiple reflections at both the frequency inside the ZNO layer because they are significant and cannot be ignored. And the thickness of PT layer is around 200 nanometer, and therefore both incident and SHG waves will be fully blocked and reflected by that PT layer. So for those just now I explained, for that this is the diagram. And now after doing a sharp ML, the experiment result can thus be fitted. As demonstrated in figure C and D, the SFG polarimeter resulted at the theta of 45 degrees, and P polarizes SFG intensity is the figure C, and the S polarized SFG intensity at figure D. And now we are going to figure E. It summarizes absolute coefficient obtained from sharp ML in comparison with cases under assumptions. So the sharp ML case yields the absolute D33 6.6 plus or minus 2.2 picometer per volt, which is very closely reported to the values for films and single crystal obtained from crystals of it's around 7.15. This indicates that film under has a good quality and with low optical loss. Comparing these results from a sharp ML with those of KS and no PFB, the cases, the obtained nonlinear susceptibility are greater exaggerated by one order of magnitude. This is why this is because these total SHG signals were attributed to single propagation of nonlinear polarization from top to bottom surface instead of multiple bounces. To compensate this path difference between NMR and FMR, the nonlinear susceptibility have to increase it, leading to DSFG of nearly 10 times higher than the actual value. So and here Ks means Kelvin symmetry and NMR means no multiple reflection of line wave and nonlinear inhomogeneous wave. And here FPV represent nonlinear polarization generated by mixture of both forward and backward waves are ignored. And, by this case study of ZNO thin films highlighted by the necessity of more general nonlinear optical model because of increased complexity of as more materials are involved in the heterostructure. For example, let's SHG has widely applied in characteristics of 2D material on top of SiO2 by Si. Its substrate which is highly reflective in the visible region. Nevertheless, the multi-reflection of heterostructure is often assumed to be negligible. And as more binary ferroelectric semiconductors are being discovered, such as ALSC and ALB, those are optically second harmonic generation as a non-destructive method will be unique tool for probing ferroelectricity. And this case study shown some kind of highlights and the capabilities of sharp ML not only in handling various probability geometry, uh, and that goes beyond the well-established marker fringes method, but also in modeling heterostructure near the Faraday-Petrov condition. In particular, the analytical and numerical approaches enabled by sharp ML provide a versatile solution for the purpose of material characterization and numerical solution. So thank you, sir. This is thank you, sir.
So hi, this is Dhruv, and in this segment of project, we are going to see the anti-parallel and parallel spontaneous polarization produced by ferroelectric domains by comparing normalized intensities of four cases. Where in the first and fourth cases, we would be using Li-NV3-1120 crystals with opposite anti-parallel and parallel polarization incident directions, and in case two and case three, we would be using same incident polarization anti-parallel and parallel rays with quartz layer who would be creating a difference in who would be creating the difference in the intensities of reflected and transfer space of 2 omega frequency. Our incident wavelength would be 0 degree and with a wavelength centered at 1.55 micrometer, and we would be desiring to see that the results that in case 2 it would be constructively built constructive interference, and the intensity would be built to the maximum, and in case 3 would be see that the intensity would be shuttered down to some extent, and case 1 and case 4 would be same as there is no quartz layer between that. The first k omega frequency is this, and nonlinear is this. Nonlinear 2 omega, nonlinear 2 omega. We would be desiring to see the first and fourth as plotted as plotted as plotted as blue and red here. Blue and red, blue and red, blue and red, blue and red. The one with fixed analyzer and rotating polarizer, and the other with fixed polarizer and rotating analyzer. And we would be seeing constructively interference in this case 2 and destructively in case 3, opposite in both. So we will be moving to the demo part. Opening Mathematica or Sharp ML, setting material properties 2v3. Okay. Updating it. Mathematica taking its time. So we'll be introducing third layer, no quartz layer in the first, so it is lagging, showing its true colors. Okay, the update. For second part, yeah, 50 micrometer, and we will be using Miller indices, and mathematical part would be showing us later. So all fine. We're moving with SHG simulation. First, rotating a polarizer and fixing analyzer with 0 degree. And here we see different graphs. Oh, sorry, 45 degree, so 0 degree. So yeah, here the polarization is around 0.8. I can zoom. Oh, no, I can't. Oh, you can. I think so. Yeah. It's zero point 0.8, around 0.8, around 0.8. And after changing the SFG polarization to 180 degree, we would see different. We would see the same output as it is. This is case 4. We would see the different 4. All right. Now we would be fixing polarization and rotating analyzer and checking it at 0 degree and 180 degree. At 0 degree, and at 180 degree. 1 second. For 0 degree, it should be showing 2. Or 80 degree. Yeah, for this is 2, and here we will see 4. Yeah, here we will see 4. So this is transmitted SHG, and this is reflected SHG, and they are showing the same intensities with pi by 2 phase difference for 2 omega and omega respectively, and for 0 also we can check. So this is case 1 and case 4 showing us at the same time. All right. Now we're moving to the case 2 and case 3, introducing a quartz layer, which would be showing us a significant amount of the difference in intensities, and we would be analyzing it with the graph plots, changes in uh, constructively in the 0 and destructively in 180 degree polarization, and but not in the case 1 and case 2. Mathematica demo, setting material properties, adding one more layer, updating it. Mathematica taking its time, introducing third layer, lagging shift, setting the thickness to 35 micrometer, using crystal physics direction in this one, updating the values. Mm, 50 meters, all good. SHG simulation. This is for 0. Now we would be changing the SHG polarization to 180 degree. And we would see the change. And there is like this is around point around 1, and this is point 0.8, and for 0 degree. Hmm. For 0 degree it's around 1 and it's around point 0.8. All right. We would check for the different now we would see the change, I guess. Change. Yeah, here is a change. The transmitted SFG is now increases to around 1, and for 180 degree we can also, yeah, it's decreasing. Yeah, let me check it one more time. I'm shifting to 0 to 180 degree. Reflected is increasing. Shifting to 0 to 180 degree, reflected is increasing, and I'm shifting to 0 to 180 degree. Okay, it's, yeah, attack here. Shifting to 180 degree, it should decrease. Yeah. This is case 3 we are talking about. Yeah, it's, yeah, the transmitted is increasing from 0 to 180 degree. We would see the decrease. Yeah, all right. So this is the SHG simulation, and we can also see the practical analytic expression, which we'll be seeing in my Python notebook. This is for case 4. We have to do normalization for finding the perfect output. This is the plots for SHG simulation. I would like to see for 180 degree, and we would be finished with this. I'm going to see the outro. This is for 180 degree 0, and we would fix analyzer, rotate polarizer for 0 degree first, and fix compressor. Okay, fix. Okay, it's lagging again. Fix this and fix. Okay, 0. This is for 0 case, and for 180 degree case. Yeah, let me take the screenshot. Okay. This is for case 1. Case 2 and case 3 of this analytically. Okay. I would be checking the analytic expressions for three-part materials, and would be getting the similar outputs. Just for sake. Third would be here. Alright, update. Okay, okay, alright. Moving to SHG simulation. Moving to practical analytic expressions. 0.63, 3467, 0.544, 0.54 for 0, 180 degree. Let's check it for 0, 0. For 0, 0, it's this. For 0, 180, after fixing analyzer and rotating polarizer, that's like, no, that's not like it. For 0 case, you can see that the values are repeating themselves for the case 1 and case 4. And we can see it in graph also, in analytic form also. All right, now we're done with this. We see the results we get with this. Okay, for the in contrast, by placing the quads below the LNO, the corresponding SHG corresponds between case 2 and case 3, showing a clear change. We pick IL1 nonlinear 2 omega 0 for comparison among the 4 cases 70. Since the phi is 0, the light polarization omega and 2 omega are parallel to the ferroelectric polarization PS of LiNBO3, giving rise to the largest SHG intensity. The intensity of the case SHG waves in case 1 and case 4 are the same, while they are different in case 2 and case 3. This is because the nonlinear waves generated by LNO KL2 omega and quads KQ2 omega interfere constructively in case 2 and destructively in case 3, as we can see in this graph. Thereby, the two ferroelectric domain states Li and V3 can be differentiated by measuring the SHG intensity with the aid of a quartz reference layer. Beyond this example, okay. Now we will moving with the outro part. So we have analyzed nonlinear optical analysis of multi-layer systems, including slabs and heterostructures, extend to arbitrary materials, properties such as symmetry, absorption, orientation, and dispersion. Sharp.ml also allows multiple reflections for of both inhomogeneous and homogeneous waves at omega and 2 omega frequencies, editable heterostructure schemes for versatile material system, integrated maker fingers for polarimetry's capabilities, and fixing probing conditions for both transmission and reflection geometries. We have seen the 5 material system, namely alpha quads with AU coating LIN with KTP and ZNO PTA A23, and chosen to benchmark sharp axle against our experimental measurements, and sharp ML that had shown some analytical improvements in the data, and also it is better than the other traditional methods used, and it is showing analytical better results. It can be used for betterment of calculations in the future of optics. All right.